Okay, well, welcome to the February meeting of the Radio Astronomy Special Interest Group for TAAA. My name is Sandy Nichols, and I am going to very quickly turn it over to Gary to talk about cantennas, I think. Is that what you wanted to do first, Gary?
Sure I can.
Yeah, I
Did you
got it.
want me to jump right into it then?
Unless you guys have something you'd like to discuss first, like any lingering questions from other sessions. Anybody have any issues? Nope. Okay, Gary.
Okay. Let me share my screen. If you give me the ability, I can do that. I'm going to send a request.
Oh, I'm sorry, Gary. I didn't set you up here.
I know.
Um, does that help?
Yes, it helps very well. All right. So, um, you guys, if you have your and you can see my screen obviously, but can you also see some of the images of each other that's available?
Um, I can over on the side. Yeah,
Yeah,
there.
if you just get that real big, I just want to show you my Cantana again real quick before I share. Actually, let me stop sharing and then I'll do it that way. All right, so here's the Cantana. I've got a little dovetail attached using these incredibly high sophisticated ties. And I think I gave all the measurements to Vince, and he said it seemed like it's the right, everything was correct, but you can kind of see how big it is. And I was following some plans I found online. I've not been able to find that website anymore. I don't know what happened to it, but they actually had they were recommending another, even a bigger thing funnel to attach to this end here, which I didn't do. But I've got the
Oh yeah.
connection right there, and you can kind of see it at the bottom, that little shiny, that little monopole hiding in there. It's about 5 inches long. So what I did today, and I did this a couple days ago too, I set up my 1 meter dish on my iOptron mount, and I got that lined up with the sun, so I knew exactly where it was pointing. Then I took some images or some measurements of uh, M11. Let me share my screen. I can start showing you some pictures. M11, M42, M93, M27, and MGC 436. So let's start with, let's get this out of the way. All right, so this is M11, 30-second exposure taken with my 1 meter. And I did that today, and I had some RFI right over here. If this wasn't there, this peak would be much higher. This is, again, a
Mhm.
signal to noise ratio. Then I stuck the Cantana on, and this is what I got. There's that same
Oh,
spike, but you can see it picked up stuff. I didn't do this right. Hang on. Let me do it this way. Go back out. So here's the Cantana. See the difference? How fast is this refreshing? Pretty fast, or is it slow? Click,
oh yeah, yeah.
click. So here's what the 1 meter. You can see there's more structure over here and a little hump. With the
Yeah.
with the Cantana, it's kind of washed out, and the hump is sort of hinted at there. You can kind of see it maybe a little bit, but it's
Oh,
not really there. So there is a loss of resolution for sure, but it is picking stuff up. Let's go to M42.
oh,
Oops, sorry, that's M27. Let's go to M27. This is with the Cantana. I got really good signal to noise today. Oh gee, this is not the order I wanted to show it in. All right, let me, not sure why it's doing that. Let me just do it this primitive way. Let me go back. I'm going to close this. Come on. Go ahead, close. Away. Away. All right, so here's M42. I took this at CAC the last time I was out there. I had some RFI right in this area, and I told it, this is a Virgo. I told Virgo to blot it out. So I got really good signal to noise. That's M42. And here it is through the Cantana. Let's see if I can go to it, if it'll let me take it there. All right, that's the Cantana. That's with the 1 meter.
Oh, okay.
That's with the Cantana. So it almost looks the same. So it depends on part of this. It depends on how much other stuff is in the field of view. I think the Cantana with that size is giving me a 60-degree field of view. So it's picking up a whole bunch of stuff. But wherever M42 is, it's located near the Milky Way. There wasn't a whole lot of different stuff, if you will. So that's the Cantana again. And this was a 5-minute exposure.
Wow. So Gary, I got a question if you can hear me.
Yeah.
So am I right in thinking that this is more of a product of the field of view, the information versus the Cantana versus the 1 meter?
Yes.
The field of view seems to be a big factor in what you're actually looking at, or if you're looking at a galaxy, obviously you'd have to have a really narrow field of view if you were just interested in that one object. But this is interesting stuff. So the Cantana's got a 60, where the other one's got quite a bit less then.
Yeah, the 1 meter's got a 14.8.
Yeah.
This is about a 60 degree, I believe. So again, here's with the 1 meter, and then shoot back over Cantana. You can see that it's radial shifted a little bit away in both cases. That's the Cantana. Let's go back to the 1 meter. You can see it's just a little bit to the left of the dashed line there. That means it's approaching us or receding from us a little tiny bit. All right, that's M42. Let's look at, let me just close this. M93. This is M93 with the 1 meter. Nice hump. This must be a spiral arm, I think. These are, again, receding away from us. And let me see if this brings up the Cantana version. It does. So there's the Cantana. Now, I had some RFI over here that suppressed the height of the that we're picking up. Again, this is signal to noise. But the takeaway is this whole area here is kind of washed out. It's represented by this little curve here. This is that bump. So a lot of loss of resolution, but you can still pick stuff up. So that's again with the 1 meter. And that's with the Cantana.
All right.
All right, let's move on to this next one. This is NGC 436. It's got, it's approaching us. This is about 30, 40 kilometers per second, right in through here. And I believe these are 2 spiral arms that we're looking at, or at least certainly this might be one. Now, when I did the Cantana, I had some really bad RFI, huge RFI, and this is it. This little sad little bump. So that, it's almost not even worth showing, but I just wanted to point out, if you got RFI, at least with Virgo, the signal to noise ratio gets affected dramatically, as you would expect. So let's go back. That's with the 1 meter. And then, I mean, you can see that there's something over here, you know. So it's picking up something, but again, the resolution just isn't there because we have too much other parts of the sky that's essentially washing it out and blending in together for this kind of a composite signal. The last one is M27, and M27, I did that one today. I had RFI right over here. What you can see is a part that's receding and a part that's approaching in that part of our Milky Way. And the Cantana, for some reason, I did not pick the RFI, and look at that, boom.
Wow.
So there's something about the Cantana that it didn't pick up the same RFI, which I thought was kind of interesting. This whole area right in here. And it was kind of pointing in a kind of southwest, but kind of up. So I'm not sure. Maybe there's a side lobe was picking up somebody's, maybe picking up my router, my wireless router that's in my house. I'm not sure. But the Cantana, for some reason, didn't see it, and its signal to noise was really high. And you see that second bump there. So I think the moral of the story is the Cantana can definitely see stuff. And it's a very cheap way to go. You can build that stuff, just buy the parts at Home Depot or Lowe's and put it together.
That is amazing.
So again, that's the Cantana, and this is with my 1 meter with RFI. Now, if I had more time, I could have done the plot to wipe this whole section out, and this would have been much higher up.
Hmm.
But I didn't. I was doing some other things today.
How do you do that, Gary?
Um,
What do you do in the script? Something? Do you do
yeah,
something
there's
in
in the Virgo plot function, you can designate regions where there's RFI that it'll block out. It'll just take it out. And that's what I did with the with this M42. You can see right in here, this little empty spot here, and over here there was some. And I just told it to knock them out. And when they did, and they were quite significant, and the peak was probably over here someplace. And when I took them out, the signal to noise went way up. So if you have RFI, and if you're using Virgo, it's a really cool way of enhancing the image, if you will. Yeah, that's what I was going to show. You can actually see where I blocked it out here too, on this waterfall and on the left here.
Oh my gosh.
And I still don't know what this graph does. It's power versus time. I have no idea what that. Still haven't figured that one out yet. So I think the Cantana idea is really worth doing. I think it's worth pursuing. It's very inexpensive. Like I said, hang on, let me. I don't know where my control just went. I'm gonna turn off.
Well, you made a very nice Cantana there. That's a lot better looking than
Here you
some of
go.
the ones I've seen, because you can make them just out of a coffee can.
Yeah, this is just your standard. I think it's a 6-inch ductwork, and then I got this little end cap that fits right in. And I just use sheet metal screws. I don't know if you can see the sheet metal screw there.
Yeah.
That holds it in. And then this is just like a collar that goes around it. I screwed that on. And the only real big deal was putting on this little guy. You solder the your monopole copper. It's like a 2 millimeter diameter copper wire that I had. I just soldered it to this guy, and then use little sheet screws. Or actually, I think I used. Yeah, they're just sheet metal screws. Hold it in. That's all it is.
Well, that
high-tech dovetail attachment here.
So that connector you have, let me think there. So you've got a connector connected to your pigtail, and then coming out of it. So the pigtail is connected to one side of that, either the center or the outside of it.
This just screw. This right angle thing just screws on. So that's all it is.
Yeah, and then but on the inside, that pigtail is soldered to something.
Yeah, it's soldered to this thing.
Okay, so it's soldered to the outside. Okay.
Yeah. So if you take this out, there's a center hole that you put the little piece of copper wire and you just solder it in place. That's all you have to do.
It's soldered to the center wire of that plug, right?
Yeah.
It's not touching the
Not touching the frame.
ducting at all.
Yeah, it's
So how big is
insulated.
the hole in the duct for
What?
that plug? You drilled a hole in the plug. You drilled a hole in the side of the ductwork
Yeah.
to fit the plug,
Yeah.
and so the copper wire goes through the hole but doesn't touch any of the ductwork.
Yeah. If you see, you can see
I
the.
see it. I got it. Okay. Yeah. Thank you. Now this, I'm still trying to understand this a little bit. This is the entire antenna assembly, or is
Yeah.
this like just the feed horn?
This is it.
This is it.
Yep. I stuck it on my.
And you just mount that and point it.
Yeah. Just point it to the sky. You can just just put it on the ground, pointing
Wow.
straight up, and it's
Okay.
gonna pick stuff up.
Okay.
Yeah.
All right.
It's like I said before, it's a huge field of view.
Yeah, but
So you're getting a whole bunch
you
of stuff
showed
all
me what
mushed
you
together,
get.
but
Okay.
it works great. So
Now, is there any significance to the diameter of the ductwork?
yes,
You
yeah,
said
there's
6 inches.
you got to pick the right size. I'm getting a ruler out. So this ductwork is it's almost 6 inches diameter,
Okay.
and that's
And
about right for the H1. And the distance, the factors you got to worry about is the diameter,
yeah,
the distance the monopole is to the back. That
yeah.
has to be I think a half wavelength. So if I measure it, it should be around 10 millimeters. Yeah, it's 10
10
millimeters
centimeters, you mean?
or 10 centimeters.
I see.
And then I think the length from where the monopole is to the end, I think that has to have a certain multiple of wavelengths, but I'm not sure.
Okay. The diameter, does that have to be a multiple of the wavelength, or because you said it's about 6 inches, so that's
It's,
that's 15 or so
yeah,
centimeters,
15 millimeters. So it's
15
about three
centimeters.
quarters.
3/4.
Yeah.
Would it work better if it was exactly one wavelength, like 21 centimeters?
Oh, geez.
I don't think so.
No? Okay.
I've seen various websites that talk about the dimensions, and the width is critical. If you get it too narrow, too large, it's not as effective.
And so 6 inches is the,
Yeah, 15 millimeters or centimeters.
okay.
There is a range. You don't have to make it at 6. There's a range that it'll work in, but if the width is different, then you use different calculations for where it comes from the back end and also how long the pigtail is.
I see. Okay.
He said, just like he said.
Well, they've got little calculators online you can bring up and you can say, okay, this is what I got. And again, gives you some of I think that's what Vince might have been using when he was looking at these. He also had something that he talked about, an extra wire, I think that he was putting on someplace. I don't remember exactly what it was doing, but you can get a little fancier with them, I think is what the moral of the story is.
Hey, when I
Isn't it
build
like
one, I'll be
loop?
happy if it just works.
It does work. It obviously it works.
Yeah. Yeah, I did it today. I know he had sent an email to Sandy, you and me, and I think he included Dan on it or something. I was going to post it to the forum, but I was going to suggest I was hoping he would be here today to suggest that maybe he should put all that stuff out there, all that information he's got, the calculations and things. So I think that'd be beneficial for all of us. But he's not here, so I'll shoot him an email and suggest he do that. I'd rather have him do it than me. I was thinking of putting it out there myself, but I thought maybe he should do it.
Yeah, that's a good idea.
Yeah. But and I'll see if I can find that website with the calculations that I used. Well, that confirmed what I have. Let me just make a note to myself to get that. And if I find that, I was going to suggest this to everybody. Let's start using the AAA forum for discussing questions and stuff. I mean, why not?
Mhm.
Give the
Oh.
astro imagers a run for the money.
I had requested to get on that and I never got a response. Maybe I wasn't contacting the right person.
I thought it was automatic, actually.
Yeah.
I didn't think he had to intervene at all. I think it's Ben Bailey is the one who manages it, right?
I don't know.
Yeah, I think he's the one. So,
Hmm.
okay, any more questions about Ken Dennis? I have one.
Okay.
Does this have any potential for one of the TAAA sites?
Yes.
What do you think would be a good way to do it?
So my thinking is we could build one of these little guys. And if the club maybe can purchase a Sawbird and an RTL SDR, and the cable or a USB cable, whatever, then all the user would have to bring is their laptop and have, let's say, SDR Sharp or some other application running on it that they can use to talk to it. As far as mounting it, we could initially just have it sitting on the ground or prop it up on a rock or something and play with it that way. I mean, ideally, it'd be nice to have some kind of like a cheap little tripod. I know that the club's got a whole bunch of tripods sitting around.
I have so I handle all the donated equipment that the
Oh,
club
okay.
takes in. I handle that inventory. We have a bunch of tripods, everything from lightweight camera tripods to heavy duty tripods for things like C11s and things like that.
Oh, wow.
I have an old Cave Astrolo mount that could hold like a 20-inch telescope that's just sitting around doing nothing. So we have lots of mounts and tripods and things. I'm sure we could figure something out. Problem is, where would you store this thing if you were going to store it out at CAC or TIPA? Where are you going to put it when you're not using it?
Put it in the RMO building.
Yeah, you could do that, I guess. You'd want to talk to the CAC director about that.
Yeah, there happens to be one that might know here that's on our Zoom session here, Mr. Rose. What do you think?
Now we have a storage container at TIMPA where we store club equipment, and so storing something like that at TIMPA would not be a problem.
Well, we're getting ready to build the enclosure for the Henze telescope, and it's currently stored in the amphitheater container. Once it's out there, there'll be a lot of room. That's a 25-inch telescope. So that would be a place to put it, possibly.
But this is the type of thing where we could build more than one of them. We
Yeah.
could put one out at TIMPA too.
Mm-hmm. Yeah.
Yeah, the Temple one would probably get a lot of use being that much closer to town.
Yeah.
That's true. You can use it during the daytime. You don't have to be there at night.
And I don't think it would get that much RFI out of Tempo, would it?
Oh no.
No.
Well, they got the radio control guys flying their airplanes.
Yeah,
Well, yeah, but they don't do it at the same time, do they?
Well, they're out there in the daytime.
Yeah.
They're not out there very often at night, though.
No.
Well, it's true. Our antenna will work any time of the day.
Yeah.
Hmm.
But
Well,
I mean, the radio airplane guys, they're a couple hundred yards away to the north, and like I said, they're only flying in the daytime.
Hmm.
But there's only one or two of them that fly at night. They're very brave. They got lights on their planes. They
Yeah.
fly at night, but I only see them out there like once or twice a year.
Yeah. And most of the objects you would look at would probably be
Yeah, I
southeast
would
and
think
west.
so.
So you'd be pointing away. So I don't know what there's this thing called side lobes that are diffraction pattern rings, if you will, that the radio telescope has that could pick up some stuff off to the side, but unless you bring it out there and test it, I don't know how it would perform, if it'd have any problems at all.
Hey, Gary, those model, I used to fly model airplanes, and they're only allowed by the FCC to let put out 100 milliwatts. That's as much as they can put out.
Hmm.
And they're using a spread spectrum scenario is what they're using.
Right.
Yeah.
well, I think what would be interesting to see too, if we did get any RFI, is how you got that method you used to get rid of it using Virgo.
Yeah. It's really easy. Um,
Yeah. Okay, well, just some thoughts about it. I'm sure we're going to get asked on occasion about getting some presence out at one of the TAAA sites. So,
right.
okay, well, our big topic for tonight was the Cantena. I kept putting something on our agenda to take a look at that was one of Dr. Wolfgang's one of his presentations on exotic hydrogen. And I was just looking at it earlier today, and he talks about exotic hydrogen and masers of various sorts. And this is all for radio astronomy. So I thought if you are interested, we could take a look at that. Also, one other thing too, maybe I should show this first. Uh, the radio astronomy doesn't all have to be plots and diagrams and calculations. Actually, there's some part of it that's kind of fun. One of the Astronomical League's projects is that uh, you record meteor trails, and you can do this, of course, in any kind of weather or any time of the day, too, for that matter. And once you get the hang of it, once you find a frequency that you can get this working at, you can really run it about any time, and you see a lot more meteors than you even do visually. So
Hmm.
I thought I would do is just give a real quick example of how this shows up. And all that you need to do, first of all, let me ask, does everybody have an SDR that they're working with?
Yes.
Who
Okay.
doesn't?
Yeah, is
I,
anybody
I, I don't have one yet. I haven't started on any of this stuff yet.
Yeah, John doesn't have one.
okay? Do you have one, Bob?
No, I haven't got one yet.
Oh, okay. Well, all it really is needed to equipment wise is you need the antenna, of course, LNA, and the SDR. And then, of course, you have to be viewing this on your computer. The trick isn't so much in the hardware setup. The real problem is finding a frequency that works, and I'll explain that in just a minute. But let me see if I can find, yeah, I think I can find my thing. This is a video that I took. It's about 5 minutes long. It's a video that I took. It takes about a minute before you start seeing much of anything. And what you'll see is it's monitoring a particular frequency. It's actually in the FM broadcast band. It's 107.39, I think. And the principle is this. When the meteor comes through, it's ionized, it's laying basically down an ion trail, and that trail acts as a reflector for a station that you normally don't pick up.
Hmm.
And so the FM radio broadcast, it hits that ion trail and reflects back on down, and that's what you're picking up. So the real problem, I've been looking for frequencies for weeks, months actually, because you're looking for something that you normally can't see, which means you typically like maybe pick a station that's, I don't know, for me, like over in Portland, Oregon or something, that there is absolutely no way for me to pick up here. And I sit there and watch that frequency. And if it doesn't work, go on to another frequency. And the other problem is that you need to have what you're really looking for is a station that's using analog, not digital signals or technology. So it's a real challenge. Everybody who does this, the problem is finding the frequency. But let me show you what it looks like when you get it working. So I'm going to share the whole screen. Also, I'm going to share sound because you'll see as these things come through, they're making a sound that's quite distinctive, and they change frequencies also depending on whether, I guess when it's going over the station, because of the Doppler effect, when it's approaching the station, it's one thing. When it's going away from it, it's a different one. So let's do this share and see if we can get this working. Whoop. I may have to go directly. Oh, no, that's coming up with YouTube. Okay, there's the first one. But in about a minute here, it'll really get going.
Is that another one?
Yeah, there'll be a bunch of them coming through. I think this is a whole meteor shower. This is about 2 days ago.
That's amazing.
Be a big one.
Cool.
That's amazing.
Notice how they're changing frequency.
Yeah.
That's pretty neat.
They're kind of fun, it's like taking your telescope out and just, looking at stuff and just enjoying it. So I just wanted to show that because this radio astronomy stuff isn't just all calculating and doing the stuff, the approach we've been doing. It's kind of fun, actually.
What antenna did you use for that? What kind of antenna was it?
Oh, well, now that's another story. So
Uh-oh.
this was a very good antenna setup. This wasn't in fact I intend to try it out with some of my lesser antennas, but this is the antenna, the what do you call that? It's the phased dual dipole array that I made for the Jupiter project.
Oh, that
Where I was describing how you use two dipoles and then you bring them down into a combiner and it comes in like that. And it was also a very good SDR that I was using. I was using an SDR Play one. But yeah, that phase dipole thing can really, really pull them in.
Wow.
So and in fact, I'm not even sure what station it was responsible that I was getting the bounce offs of. It could have been with that particular antenna, I've looked at what it's picking up. The station could have been quite a ways away.
Yeah.
There was one part was like a real thick
Yeah.
section of white. Was that one as well?
Yes, it was. And the to me, it's like, seeing one of those Perseid meteors come through that leads down the big smoke trail, great big
Yeah.
thing. Yeah, that was. It was all part of that. It was like a meteor storm going on. This was like 7:30 in the morning about 2 days ago. So,
Wow.
Jeez.
Oh, cool.
and the other thing is they come through in waves. Now, I had finally the night before I'd been monitoring this frequency. And then I noticed off on the side, not the direct frequency that I was monitoring, but off on the side, I would occasionally see a blip coming through. So I moved over to that frequency and watched it and saw that about every 15 minutes I would just get this light blip coming through. Well, it turns out one of the things they tell you about watching for meteors is that your best time for doing it is going to be between 3 o'clock in the morning and 9 o'clock in the morning, because as the Earth is turning, you're basically kind of turning into where you're going to get them. It's actually much better than at night. So I figured, well, if I'm seeing these little blips at night, I guess I should get up and fire this rig back up, maybe at like 4 or 5 in the morning and monitor it. And so that's what I was doing. And sure enough, as it got closer, after about 6:30, it started really coming in. And as you can see, there's no doubt about it. It's not like, sometimes you'll see an RFI, you'll get a little bit of a signal coming off on the side or something zooming through, but these are really unmistakable.
Sounds like
But
sounds like having an all sky camera would be kind of a cool thing.
with the correlated with the radio?
Yeah, all sky camera, and you're just monitoring activity, and then you have that STR on and go, yeah, these are definitely, you can look at the different trail patterns, and if you really want to get into it and say, yeah, this is, these yield more signal than other ones, you could compare the different brightnesses and things like that.
Well, there's a whole group around this radio astronomy with meteors, and what they do is during the meteor storms, like the Leonids or something, they actually start these monitoring watches, and they post their counts to this discussion group. I've seen them, and so they it's really kind of fun. That's the way they sort of, it's like a star party, but for radio astronomer meteor people. So.
So the meteors, they probably aren't the ones that we see overhead necessarily. They're probably closer to where the radio station is.
Yeah, that's the point. Yeah, see, I was going to mention that too. You're right. In fact, since I don't really know even what radio station I'm picking up, and if you think about the bounce that you're getting, they tell you when in the project that you're doing for this that you should be looking for something that's actually quite a ways away, like a station that may be like 700 to even a couple thousand miles away, depending. So,
Wow.
Yeah, that's amazing.
yeah.
And these are FM stations that we're listening to, not
Well, that's what I was focused on in that one. But I got to tell you, I spent weeks looking in TV frequencies.
Hmm.
So, like Channel 2 is a real big one that's used by radio astronomers out on the East Coast who get into this business of looking at meteors, because there's a big, strong transmitter up in Canada somewhere. And all along the East Coast, they can pick this up when the meteor storms come in.
Hmm.
So, but out here where I live, if you ask people, they'll say, well, we really can't find anything. So a guy with the Astronomical League gave me a suggestion. He said, and what he did is he looked at Spokane, which is near where I live, and he looked for kind of an open spot in the spectrum, one that wasn't being used by anything in Spokane. And then there is a site that he went to. I've got it in an email he gave me, where he started looking for stations that were quite distant from me, but that wouldn't overlap with anything in that FM spectrum. So he suggested this 107.5, and I started looking at it. I was monitoring it 107.5, but then I saw this action off just a little, very close to it. So I was off in a sideband area. So anyway, it was pretty, it's fun, you know? So it's
Yeah.
like you've got a radio telescope. It's all you have to do is turn your computer on and start monitoring it and see if you can catch some meteors. And people who do this, apparently, they'll have it running in the background while they're doing something else in their office because, of course, you don't have to be looking at your computer. You can hear them.
Right.
So anyway,
Cool.
okay. So are you folks ready to hear about exotic hydrogen?
Sounds exotic. Yes.
I'm ready.
Okay. I may need to take just a minute to find this. So be
If
patient
you're not
here.
going to discuss anything else before this video, I'm gonna head on out.
I was going to show the 8-foot dish I got recently, if you guys want to see it, for $49.
Why don't you do that? Well, I'm
Yeah,
trying to find this.
$49. Let's see that.
All right, let me share. I'll share my screen real quick. Yes,
Oh,
it's got a tear right in here. You can kind of see it, and a couple little funky parts. But Bob helped me bring it home. It's 92 inches across, and I'm hoping to build a waveguide with what they call it a scalar ring, which just looks like a ring around the center feed horn thing, to see if I can pick up neutral hydrogen and somehow figure out how to mount this thing because it's really heavy. But $49.
good deal.
Okay, I'm done. Back to you, Sandy.
All right, I'm gonna check out, guys.
See you around.
Thanks.
Okay.
Okay. See you, Doug. All right, let me share here.
No.
Where I'm looking in the same direction. So it's moving away from me, but exactly in the line of sight. And that allows me a simple calculation of how far is that cloud away from the galactic center. As I said, it's called a tangent point method. I can't, for timing reasons, explain that in detail in this overview. What I suggest, but there are many, many explanations of that. I have listed one here in the below, a web resource that you can have a look, but there are others. If you put in tangent point as the search in Google, then you will get a number of explanations. The basic thing here is that I can.
Okay, that's not quite the point I was looking for. So let me continue on a little further. Let's try this.
Galactic source. And I'm showing here the work from Jean-Jacques Mantoux from France. He calls himself always JJ. And he has a very nice 3-meter dish. And it's a fairly sensitive instrument with only 60K system temperature. And he's recorded this spectrum, which is from the Andromeda galaxy, and another one from the M33, another galaxy. What you see here is what is typical for these type of galaxies, is sort of a double hump structure. So he did that, and I want to show that this is not so easy, because the first thing that he did was he did take care that his spectrum is very flat. So this is a 4 megahertz width of spectrum.
Sorry, I'm still not there.
Here's exotic.
normal hydrogen spectrum, but is stronger than what we can see from this galaxy. So what is this? And I call this among this heading exotic hydrogen. These are high velocity clouds. These are clouds, and I show a graph of that, that sort of come from outside of our galaxy and fall into our galaxy. And these can actually be received with a 3-meter dish quite reasonably. This is our own 3-meter dish. That's a 30 minutes integration time. And this is the high velocity cloud, which can be seen. And that, of course, is the hydrogen from the galactic plane. And that can even be done, as we have seen, with a smaller dish. There's an experiment by Job with his 1.5 meter dish. He took 5 hours integration time. So it's, he compensated the smaller aperture with integration time, and he was able to see that a little bit. So, where do those come from? There are different theories where that comes from. These high velocity clouds can either come from primordial gas clouds, which have come in a very early time and sort of are collected by the gravity field and are then falling into our galaxy. Another theory is that something has happened in our galaxy that has thrown out hydrogen, like a supernova explosion or something like that, and that's falling in again. And then there could be an interaction between satellite galaxies and ourselves. That's an unresolved question, or where do they come from? The main message here is high velocity clouds is something that can be seen with amateur size equipment. To finish off exotic hydrogen, the final mention of something which is even more exotic. These are radio recombination line. What happens there is that if you look at the scheme of hydrogen in the optical regime, you have the alpha line, which is a red line. You have a alpha 1 line, which is in the ultraviolet. A3 alpha is in the infrared. And as you go up in the energy levels of the hydrogen, you end up in spacings, which are again in the radio regime. So what happens if you are in an environment where the hydrogen gets ionized, so the electron is taken away from it, the hydrogen will then eventually collect its electron again, or somebody else's electron, and recombine, being again a hydrogen atom, but being in a very, very highly excited state. And as these excited states decay, they emit again radiation in the radio regime. And there are a number of radio recombination lines which are close to the hydrogen line, and these can also be observed. Now, I have to say that so far it has not been achieved by observing these radio recombination line with a smaller size dish. This is an example from a 25-meter dish, or 25-meter dish. This is a hydrogen recombination line in the Orion Nebula. You need something that excites that you have to have ultraviolet radiation to excite that. And you can see a fairly decent signal. That's actually comparable to the emission from the other galaxies. So it might be doable to do that with a small dish. This line over here actually is not from hydrogen, it's from carbon. That's a carbon recombination line, because you also have other atoms and they can also give rise to a recombination line. So that sort of concludes what I can say about hydrogen. If we take hydrogen, we can do mapping of the hydrogen, we can determine the rotation curve, we can observe high velocity clouds. Extragalactic, that's getting difficult, and radio recombination line is probably more difficult. And there are two areas I have not covered because they are essentially the area of bigger telescopes like ours. These are absorption spectra towards high luminosity sources and some deep space hydrogen clouds. That's the story of hydrogen. So, question about that? Rich, anything?
No, still nothing on chat. Anybody else have any questions?
I'd never heard of high velocity clouds before of hydrogen.
Hmm.
Had you or?
Not me.
Yeah,
Not me.
outside the galactic. You know, what's interesting actually, as you go along with this hobby, of course, is that you were actually able to detect things that, you know, visually you can't see them.
Oh, bless.
So, Bill, now you can use your 3 meter to explore this exotic hydrogen.
Yeah, but I got to get smarter so I know what I'm doing. But I actually am going to beam it over to, I do have a way to aim it now. So I am going to steer it over to M31 just for the heck of it and see what it does. Yeah, yeah.
Cool.
Yeah, that is, I'm thinking, Gary, I want to maybe get that SDR to work with that 3 meter dish. I'm thinking more about that now.
Okay. Let's
But
do it.
yep,
You'll have to make a new waveguide and all that for that, but
like that one there is been optimized for the 21 centimeter though. I don't know that I do need to make another one. Do I?
okay.
I mean, I don't know.
Makes 2 of us.
But yeah, yeah. But
Well,
yeah, that was very interesting.
well, I had thought that frankly our discussion on Cantennas was going to last a lot longer. We missed Vince. I think Vince was all geared up to go through
Yeah.
your calculations. I do have a continuation on that video of masers, but we could do that even another time. Do we have any knowledge of masers, what masers are?
At one time, but it's evaporated from my brain.
They're like a laser.
Yeah, but I think it's I probably will say the wrong. I think a maser is more of a on the radio frequency spectrum than it is the light.
Right.
That's about as much as I know.
Well, on YouTube, if you go on and look for radio astronomy masers, there is a fellow, he's a Norwegian guy, who was starting a project of looking at masers with his, I believe it was the itty bitty scope. It was one of our small dishes. So why don't I just go ahead and get started on that maser thing then, and I'll show you, because he has this Wolfgang goes through starting talking about different types of masers. So let me do that real quick.
So it seems like it's important to keep your signal to noise levels in
is reduced, and that's exactly what happened. That's all you need. Typically, it's an incomplete module, desperately looking for yet another H to form water. But
sorry, as you can see, I'm kind of searching around here. Start just a little bit back from where the maser discussion
is reduced, and that's exactly what happens there. And this is the reason why you can see hydrogen still with a small dipole. It's just looking at lots and lots and lots of hydrogen. Okay, let's continue by adding some oxygen to the hydrogen, and we have OH. OH is a radical, so it's an incomplete module, desperately looking for yet another H to form water, but there's no other hydrogen available right now. And this OH has 4 transitions in the L band, so in the region where typically our hydrogen equipment works, at least close by. These 4 transitions, they can be observed in emission and absorption, but really what's most interesting for us in the amateur arena are OH masers. And these are circumstances where you have a strong infrared radiation, which excites the OH to a high vibrational level, and then it decays, and then it starts to getting a inversion situation, a inversion between the different levels of the hyperfine structure, and then it starts to maze. The nice thing about OH is that in most cases you will be able to use your equipment that you have built for hydrogen. You can use it for OH emission as well. You may have to change the filter if you're using any, but that's all you need. Typically, the LNA and so on will be wideband enough, and also the SDRs will cover that. And there are a few examples which I want to show with 3-meter dishes. That's the sort of the size where you can do these kind of observations. The 3 on top are done from with a 3-meter dish from Eduard, and there are what are called circumstellar masers. So they are around a big infrared star. So the infrared radiation from a star generates the energy which makes them a maser. The other example shown here is from JJ, who I have mentioned before, but also with a smaller dish in the 2-meter class, Job has been able to observe a maser. It's sort of a weak at the limit of the acceptable signal to noise ratio, but still I believe it's a valid because the line is exactly at the right frequency. So really OH masers is something to go into once you are sick and tired of hydrogen. So just throw in a little oxygen and you're there. Other masers are also observable. There are methanol masers and water masers. Methanol masers, they are at 6 gigahertz and at 12 gigahertz, but it's more convenient for amateurs to observe it at 12 gigahertz because standard LNBs can be used. The standard LNBs have one issue, or at least the older ones, that frequency accuracy and stability is an issue. But the more modern LNBs, they have a PLL, so they have a little crystal inside at either, I think, at 25 or 28 megahertz, and you just throw out that crystal and inject a external clock, which is tied to a reference standard or whatever you may have available. And then you have a receiving system, which is fairly frequency accurate, and you can observe that. And I'll show you examples of that. The second option that we have as amateurs is to observe at 22 gigahertz. It's a little bit more tricky because LNBs are not readily available. There are some Ka band LNBs, but they're hard to come by, and the external clocking there is a little bit more difficult. The good news about the water masers is that they flare. They are very variable, but occasionally they really get very, very bright in the tens of thousands of Janskis, and they got really, really strong. Some examples of what has been done. This is our own experiment. That's with our 10-meter dish, 10 minutes integration time, methanol masers around the star-forming region W3. And the question, of course, is, well, you got this 10-meter dish. I only got a 1-meter dish. So it's not an option for me. That's it's a factor 100 in collecting area. To compensate with integration time, that's 10,000 times the integration time. So I'm at 1,600 hours integration time. So no way you can do that. Well, not so fast. If you give up a bit in spectral resolution, a factor of 5, and give up a factor of SNR, so going there, maybe I can live with less spectral resolution. Maybe I can give up with the SNR signal. Then I end up with theoretically 20 hours observation time to see that source. And indeed, Eduard has done that. He did that with a 1 meter dish, 17 hours integration time. So it was just sitting there and then tracking and tracking. And he has, because you can't collect at his location 17 hours of integration time all the time. So he had to accumulate over, I think, 3 days or so to get those 17 hours. Of course, you need a tracking setup. So he has a mount here which tracks the source, but then you're able with a standard LNB to observe a methanol masers. So that's, I find this quite impressive that a 1 meter dish is capable of doing that. Now, how about the water maser? Again, this is our 10 meter dish, 60 seconds integration time. I mean, these guys are really strong. So anyone with a 1 meter dish going for the challenge? Sure enough. There is one example. It's a different source. It's W49 in this case, and this is a bit weaker even. So this is a spectrum we have taken with 10 minutes integration time in January of 2019. This year in May, Michael Klaasen, who has a 9.3 meter dish, did that with the same integration time and again recorded a spectrum. You will notice this spectrum is completely different from this one. This is because these are highly variable. They change their spectrum, they get more and less intense and so on. The interesting thing is that Eduard, who did this with the methanol masers, tried that with his 1 meter dish with a 1 meter dish and at about the same time. So you see the spectrum is the same and he was able to do that. Unfortunately, I couldn't find out his integration time. It's probably again something like 20 hours or so to get to that. But you can see that the spectrum that is taken here with a 9 meter class dish very nicely reproduces with this 1 meter dish. Just have to have lots of patience to do that. So in summary, OH, methanol, and water masers are observable with MS2 size equipment, even with relatively moderate size. In most cases, a tracking mount will be required. So you need to be able to follow that for a long time to get the required observation time. And the interesting thing there is that it does, because these change, you can do the observation over and over again, see what happens there, because that's something that the big telescope, they cannot do that. They cannot follow that for such a long time and look at the variations. So you can actually even do some interesting in science. All right, this is my maser summary. So again, would take the opportunity to answer any question that.
So when you get tired of hydrogen, when we get tired of talking hydrogen, can take a look at some of these masers. The one that I was mentioning was a fellow in Norway who was going to take that itty bitty one and see if he could spot some of these masers. And it almost sounds like a reasonable one to go after would be a water maser, since when they can be quite a burst apparently. But you notice really he was really discussing two different telescope designs, right? Like for the masers, he kept mentioning an LNB. Well, that's what that itty bitty scope is all about. So that LNB, I think we talked about this a little bit last time. It's got the sensor in there, but it's also doing a frequency conversion and amplification of the signal. So if you look at like the itty bitty scope versus the scope in a box, those are kind of two different designs, right? Whereas when he was talking looking at the hydrogen line and the recombination lines, that was the scope in a box design doing that. That's what we've been using to look at the hydrogen line, right?
So the low noise blocks, that's your standard issue satellite dish, feed horn, if you will. But he said that you have to have a external clock because the internal clocks aren't that reliable, I guess, or that steady. That's the impression I got.
Yeah, I'd have to go back and review that. I'm not sure how I would comment on that.
Yeah.
I think you could just take, I don't know why the clock would have anything to do with it, to tell you the truth, because you're simply taking a look at a signal, right, and graphing it. Unless you're thinking in terms of like that IF average algorithm. Is that what you're thinking?
I'm thinking it's the down converter. It's using a reference signal to know how to maybe down convert it. I don't know much about this. I'm just sort of making this up maybe, but I know that the clock is used probably to set the frequency at which it's sampling the signals coming in. And if your clock is varying in terms of its it's not very precise, you're going to have a spread of frequencies you're looking at and kind of wash the object out. That's my ignorant perspective. My
Yeah, I'd
uneducated
have to think about that one for a bit.
Yeah.
Anybody else had any experience with those LMBs?
I vaguely remember, Gary, with what you just said. I was looking at those before I pursued, got my system, and I think you're right about that. That I think those LMBs can look at a lot of different frequencies, but I'm not sure again how the clock works, but that might be part of it. It may have to have a real precise clock.
The question is, does our Sawbird, for example, have a
Oh,
reference clock in it that it uses, Because it'd be a similar idea, but I don't know.
Well, it sounds like a good thing to follow up on between now and our next talk.
Okay.
Okay, anything else? Anybody want to bring up anything, or should we call it an early evening?
Call it an early evening.
All right, I'm going to turn the recording off here.
Okay.